Hi, everyone. I'm still working on the microphone issues. I don't know why it's peaking at times and why I'm getting really loud. Because if I sat here and just talked like this, my audio just gets visibly quieter as we go, and then it like jumps back up, and I have no idea why. I thought at first it was because I was moving a lot, but and so I was getting closer and farther away from the microphone. I'm not. I am like purposefully standing very, very still. I'm going to move closer now, just because I'm far away from the microphone. I have a blanket on. It's very cold in my house right now. So, area. Okay, this is kind of what it's all been leading towards. See, it just spiked again. I don't know why. This is what it's all been leading towards. Everything we've been doing. One of the classic questions we had way back in 1.1. I think I mentioned, what if sailors wanted to know how much, like, I think it was any type of liquid, typically wine, that was in a barrel. They would find different ways. Maybe they would weigh it and then go, oh, well, it's roughly, this much volume is roughly this much wine. But then you get into issues of different amounts of different, like, woods that are being used for barrels and stuff like that. So it wasn't very accurate. So people started coming up with ideas on how we could find, like, the volume of things underneath a certain curve. Liquid, believe it or not, when it moves around, creates a curve, and I'll get into why that's important on a different day. But for now, let's start talking about some type of notation that we're going to use that's going to be extremely important, that you have seen before, possibly. I'm not sure. I don't know if I've shown it to you, but you're going to see it today. Again, I don't know what's going on with the volume. I'm really sorry about that. So, talking about area, we just finished talking about anti-differentiation and integration. Now, just like take a big step back. We're going to walk away from that for a moment. I want to show you this thing called sigma notation. Okay, sigma notation. It's called that because it uses the Greek letter sigma. Okay. Oh, I'm in black. There we go. That's it. That's the name. It uses sigma notation. So here is what sigma notation looks like. It's the sum of a certain number of terms. In this case, in this arbitrary case, we're going to start with n terms. I don't know how big n is. I just know that it is n terms long. So this is what you do. You have a subscript and a superscript. Those are your indices. I is the index of summation. Okay? That's the thing that's keeping track of where you are in, like, the list of terms, right? We have a certain list of terms, A1, A2, A3, and so on. I is the thing keeping track of that. I is the ith term. It's not the easiest thing to say. Ith term of the sum. And the lower and upper bounds, also known as the indices, are n and 1. We know it's 1 because it says I equals 1. Now, the reason why we're saying I equals 1 at the bottom is so that way I can indicate to you which term I actually really care about as far as the index is concerned, right? I don't want you to think A is suddenly the index or N is suddenly the index. It's I, and that's why it's down at the bottom with the lower bound, because it's established right away. This is how it's read. Do I mention how it's read? No, this is how it's read. It's called the sum. This is the sum of AI from I equals 1 to n. So we're going to take all of these terms, every single one of these terms, A1, A2, A3, we're going to add them up all the way until we get AN, which is precisely what we're doing right here. We have A1 plus A2 plus A3 all the way to AN. That's why we're using a Greek sigma. Sigma is the S letter in the Greek alphabet, and it stands for sum because we are adding these things up. We are finding a sum. That's all we're doing. So, Let's look at a couple classic examples. These are good to know. I would definitely like make a note of them and write them down. But if you've got just the sum of I, which means as I goes through all of the terms that it could possibly be, like 1 and then 2, which is the progress. It's not going to deviate from that. It goes up by ones. It goes up by integer increases of 1. So from 1 to 6, you are adding up the numbers 1, 2, 3, 4, 5, and 6. The numbers in between 1 and 6. That's not a coincidence. That's because you are only finding the sum of your index. Now, let's start with our index at 0 instead of 1. That happens a lot more than you might think. That happens like a lot. And that's just because sometimes it's more useful notationally to show a formula where you're starting at 0 instead of 1, and that's because you want a lot of the first term to get knocked out. Like, for example, right here, if I is 0, you're going to start with 1. So going from 0 to 5 of I plus 1, you're going to plug in 0 for I right here, and you get 1. That's your first term. And then you're going to plug in 1, because 1 comes after 0. And you're going to plug in 1 right here. You get 2. That's your next term. And you're going to keep on doing that until you get to 5. Plug in 5. 5 plus 1 is 6. That's where you stop. And notice that this is the exact same thing as the sum that we were just talking about. It's the same thing, and that's not a coincidence. That's just because you shifted the index, and then you purposefully shifted up the thing that you are what's the word? The thing that you are summating? That's not the right word, but it might work. I'm going to take a sip of coffee. Bear with me. I haven't finished it yet. That's probably why I'm not speaking properly. So, let me get rid of all this. Let's talk about the third and last one for now. Let's say I want to add up. Oh, big important thing. It's a J now. That's okay. Typically, we use things like I's and J's and K's, I believe, are also acceptable. You can technically use whatever you want. There is a standard procedure to use certain terms over other variables, but I's and J's and K's are like the go-to ones. I think after that would be like S and T. These are just honestly not that important. It's just like good practice, like, you know, showing your work. It's something that mathematicians as a whole have kind of agreed on, and they're going to keep on, and we are going to keep on following that trend. So that way, when someone is talking about a certain thing, we don't have to go, oh, hold on, what does that mean? Can you explain that in a way that I understand? Everyone just automatically knows, oh, yes, that must be your index, isn't it? And then you double check and you go, oh, yes, it is. Okay. So here we're talking about J as an index. We're going to start at 3, and we're going up to 7, and we are going to square every single one of those terms. So we plug in 3 for J, and we square it. So you get 3 squared. And you do that for every integer in between 3 and 7, including 3 and 7. And you would plug that into a calculator. You would take 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Go ahead and do that right now. Let me know what you get. My internet's down, so I have to use my phone. So I'm going to add these on my phone. So I've got 9 plus 16 plus 25 plus 36 plus 49. I got 135. If I made a mistake, send me an email, post a comment on the YouTube section, so that way I can look back at it and go, oh my god, people actually do comment on these things. Okay, I should be careful about what I say. So let's keep going. Let's say we want to do a more complicated case. This time I'm using the index K up until n. That means I'm going for an indeterminate amount of time, but it's still a finite amount of time. It is limited to n. It doesn't get larger than n. So, I'm going to just plug in all the integers in between 1 and n. Now, you might be asking, when do I stop? Where is n? Is n less than 100? Is n more than 50? Where is it? And the thing is, we don't know. So here's what we're going to do. Just follow along for a second. We're going to start with 1. I'm going to plug 1 in. Okay? Okay, that's 1 squared. Everything else stays the same. Don't touch it. Leave it alone for now. Then you're going to plug in the next thing after 1, which is, of course, 2. So you plug in 2. You get 2 squared. Leave it alone. Don't touch it. Don't do anything to it yet. And then you don't know when you're stopping. So we use this term where we do plus, dot, 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 plus. And that just means that you are going to add some amount of terms in between where you just stopped and where you're going to stop at n. The thing is, you don't know where n is, so we go on for a bit. How long? I don't know. We don't know what n is. That might be something we're solving for. That might be something that doesn't exist and it's just a general form. We don't know. So we just say, hey, we go on for a little bit. There's a bunch of terms in there. They all look like these. I mean, you have the formula. You can go on for as long as you want. I'm not going to because this is the pattern. And then you plug in n. That's kind of like the period to your sentence, just like adding a dx. If your limit is n, or sorry, your upper bound is n, you have to end with n. So this next one's got a lot of notation going on. All of this notation is extremely useful, and it's actually going to pop up again. Now, let me walk you through what this is saying. This is saying from the index of 1 up until n, which means I'm going to end up with that plus dot 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 plus. Oh, look, there it is, right? Because we don't know how long we're going. We're adding up the terms of a function. We're adding up the terms of a function times this value, times this delta x. If you've taken chemistry, like I know you have, you've seen that delta before, and if you've taken or are in physics, you've probably seen that delta x right now. Yes, it does mean change, and that's exactly what we're going to end up using it for. That's like a rate of change. It's just like a derivative. None of that is like surprising. We've been talking about this whole time for a reason. So let's go through. Our first term is 1. We're going to plug in 1. Oh, look, that's f of x1. Now, we don't know what x1 is. Not yet. But that's okay because we're just going to roll with it. We're just plugging terms in. We're not actually evaluating this one because we can't. We don't have any integers to actually evaluate it with. And then the next term is 2. So instead of an I, we write 2. So this is read f of x1, for example. This one is, oh, can I do the thing? There we go. This is f of x1 times delta x. This is f of x2 times delta x. This is f of x3 times delta x. Plus an indeterminate amount of terms we don't know, up until n, where you get f of xn times delta x. This last example is massive. We will be using it. All of our examples, pretty much, when we're talking about area, which we still haven't talked about, is going to use notation that looks like this. Moving on. Let's talk about some properties of summations. You've got a sum right here of index 1 to n of some constant k. I'm telling you k is a constant. K is some sort of constant times whatever your term is. So what this is going to look like is you can actually pull out your constant out front, just like the constant multiple rule. The reason why is a little bit different from what you're probably thinking, but the reason why is, let's look at the sum of I equals 1 to n of k, a, I. Well, that's going to be k, a, 1 plus k, a, 2 plus dot, dot, dot plus k, a, n. Right? That k gets multiplied by every single term that we have. Now, watch this. If I were to pull the k out, if I were to pull the k out of my summation, then I end up with k times the sum a1 plus a2 plus dot, dot, dot plus an, because now I'm just summing all of the a sub i's. But with the distributive property, you can distribute that k to every single term on the inside of the sum. So you can just pull the constant in and out. You are literally factoring it in and out. Same thing. If you are summing the sum or summing the difference of two different terms, well, you could just summate them. I feel like that's not a word, but you could just add them up or subtract them in their own individual sums. So what this is saying is, if you want to add up like the sum I equals 1 to n of ai plus or minus bi, well, that would be a1 plus or minus b1 plus a2 plus or minus b2 plus dot 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 an, oh, forgot my plus, an plus or minus bn. And if you were to separate them into two separate summations, there we go. Ooh, completely blanked on the word while trying to make sure my notation was right. If you wanted to actually make sure that you were, adding these properly, you can always double check these. But from here you have a1 plus a2 plus dot 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 plus an plus or minus b1 plus b2 plus dot 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 b, and I forgot my plus again. Dang it. Let me come over here. Move that. I lost a dot. No! Oh, jeez. Guys, it's all falling apart. Oh, no. There we go. Hold on. I'm salvaging it. We're good. We're good. Everything's fine. So, the reason why we have plus or minuses here and we don't in the bottom is because of this plus or minus right here. So because you are adding and subtracting, and because from a certain point of view, addition and subtraction are both commutative, this plus or minus means if you add them all, well, then you're adding them all. And that means you're adding all of these instead of subtracting them. So it wouldn't be plus or minus, it would just be plus. But down here, imagine it was minus. You are subtracting the whole term, which means now all of these up here is a1 minus b1 and a2 minus b2. Whereas before, if you were just adding them, it would be a1 plus b1. So really, it could be a1 plus or minus b1. It depends on which one you're doing. Or if you're doing both, you're doing both. So these are the same, right? So if you are taking two terms and you're adding them and subtracting them inside of a summation, you can just pull them apart into two different summations. The last one I want to talk about are some summation formulas. I should be finished up here real quick. But if I wanted to add up like the number of constants that I have, like if just a c, just c, some constant c, it could be 5 if you wanted it to be. I want to add up all the 5s from 1 to 20. Okay, then you do 5, that's your first index, plus 5, that's your second index, plus 5, that's your third index, and you keep on going until you run out of indices. So you go from 1 to 20. Okay, well, that's just going to be 20 of them. So if you're taking 5 and you're adding it to itself 20 times, that's multiplication, right? So you end up just taking c and multiplying it, some constant c, and you're multiplying it by that upper bound. And remember, that's if you're starting at 1 because you want to have that number. If you were starting at 0, well, now you have an extra index to worry about. So you're not just going to do times n, you're going to do times n plus 1 if this was 0 for some reason. And that's because you have that extra fifth term to worry about. But we don't in this case. Oh, my eraser is now small. There we go. Okay, this is a really big one. If you do any extra stuff in math, or if you like to do math stuff in your spare time for fun, like I know you all definitely do. I'm getting my coffee. You might have heard of this guy called Gauss. When the story goes, first of all, Gauss was a genius. The story goes that when he was in elementary school, his teachers were having difficulty keeping him busy, and this is like in the 1800s, 1700s. You know what? Hold on. Is my internet back? Hang on. Oh, it's back, guys. My internet's back. We're saved. We're golden. Fantastic. Let's see. Hold on. Gauss. Yeah. Carl Friedrich Gauss. He was born in 1777. He is as old as the United States. He is dead, but he is as old as the United States. So, excuse me. In the 1790s maybe, not even. When he was in elementary school, his teachers were trying to keep him busy, and he was tasked with adding up the numbers between 1 and 100. And I'm not going to get into it today. If you want, I'll get into it tomorrow. But he found a really quick and easy way, and it's honestly really intuitive, to add up all of the numbers between 1 and wherever you want. So 1 and 100, that's really easy. You're going to take your last term. So in this case, if he's adding up from 1 to 100, you're going to start with 100. You are then going to multiply it by the next number, which would be, 100 plus 1 is 101. And then you're going to cut that in half. That should give you your, sum between 1 and 100. So what the summation looks like, what the summation is saying, is if you are adding up the numbers from 1, right, you're adding up all the i's from 1, right down here, until some amount, I don't know, pick an amount, then you're going to take that upper bound, multiply it by the next term, cut it in half. So, for example, let's do that 100. So the sum of I equals 1 to 100 is 100 times 101 divided by 2, which is, 50 times 101, right? I just cut that 100 in half, which is, you know what? I am going to use a calculator. I'm not feeling like it this morning. I don't really want to put up with numbers today. It's 50-50. 5,050. There you go. If you want to double check my work, feel free to start adding up the numbers between 100 and 1. Why is that red line there? Go away. Okay, sorry. Lost my cool for a minute there. Okay, next. The one we just finished talking about was adding up the numbers, the integers, from I equals 1 to n. But what happens if I don't want to add up the integers? What happens if I want to add up the squares, all of the squares? So I equals 1 squared, and then 2 squared, and then 3 squared, and so on. I don't know who came up with this one. I don't think it was Gauss. I'm positive. No, I shouldn't say positive. I'm pretty sure the next two are not Gauss, but I don't know. So we're adding up the numbers squared. So if you wanted to add up again, maybe I equals. Let's do 10. Let's keep it interesting. Do something different, and by interesting I mean easier. Of the numbers squared, you're going to take the last term, your upper bound. That's our 10 right here. So we got 10 times the next term is the next term that you would normally have. 11. Whoa, tough stuff here. We're adding 1. And then you're going to do 2 times your upper bound. So in our case, 20 plus 1. So 21. You can divide all that by 6. Now the 6 seems like the 2n plus 1 and the 6 kind of seem like they come out of nowhere. At least they do for me. I promise. Like if I were, I'm thinking about going over this tomorrow as to where this stuff comes from, because it's actually really interesting. But it makes perfect sense as to why they're there once we see it. I promise. So let's see. 10 times 11 times 21. 10 times 11 times 21. All that divided by 6 is about 385. Now, the reason why our answer is a lot smaller is because we're only going from 1 to 10 as opposed to 1 to 100. But, I mean, it is going to be larger because every single one of those terms is squared. And lastly, cubed, same thing. You are going to start with your upper bound. You're going to square it this time. And then you're going to take the upper bound plus 1, and you're going to square that, and then the whole thing gets divided by 4. This one, the formula for it looks a lot more intuitive. You square it, so you have to cut it by 4. For some reason in my head, that makes sense, probably because, 2 and 2 makes 4, so square and square makes 4. And from a certain point of view, that's right, but also from another completely certain point of view, that makes absolutely no sense whatsoever. So, let's I don't know, maybe just 5. You know what? No. Actually, let's do 10 again, so that way I can show you how much larger this is going to be since every single term is going to be cubed. So we're going to cube all of these. Okay. Well, that means we're going to take 10 squared times 11 squared divided by 4. So let's see. We've got 100 times 121 divided by 4 is, oh my God, it is 3,025. That is almost 10 times larger. It's quite substantial. So anyway, that's it. Those are, let's see, are there more? No. That's sigma notation, kind of in a nutshell. I definitely recommend looking up other videos on sigma notation, other ways to get used to it. And honestly, the best way to really get used to sigma notation is just doing it, which is what we're going to start with tomorrow. Okay. If you have any questions, I would, you know what? Here's example 2. Give it a shot. Okay. I want you to try it. I'm going to jump in with it tomorrow, but I want to see where you get with it first. Even if you get to like, well, I mean, I tried it, but I had no idea what to do. It's in your book. You have the digital copy. I know you don't have 4.2 like physically yet. I was supposed to give that to you yesterday, but we didn't have school yesterday, and I'm not here today, and neither are you. Anyway, okay. I will let you go ahead and try this example. What's the word? I hope you have a good rest of your day. I'm going to upload this now. Email me if you have any questions, okay? I hope you have a good rest of your day, and I will likely, hopefully, fingers crossed, see you tomorrow.